Take a single electron, just one, hold it in your hand, hypothetically, because if you actually did this, you'd have bigger problems than a YouTube video. Now shake it, just wiggle it back and forth, a few centimeters, a few times a second. Something leaves that electron the instant you move it. Something travels outward at exactly 299,792,458 meters per second, in every direction, forever, whether anyone is there to catch it or not. That something is light. Not always visible light, depending on how fast you shake it. It might be radio waves or microwaves or X-rays. But it is, without exception, electromagnetic radiation. And here's the part that should bother you. The electron didn't release anything it was storing. It didn't have a light cannon hidden inside it. Before you moved it, there was no light. After you moved it, there was. You made light out of nothing but motion. If that doesn't feel strange to you yet, give it a minute. It will. Because the honest answer to why does shaking a charge create light is not something most explanations get right. Most of them wave their hands, pun fully intended, and say charges create fields, moving charges disturb the fields, disturbed fields are light. True, technically. Also almost useless, because it explains nothing about why a disturbance in a field should be able to detach itself, travel across the universe for 13 billion years, and still carry energy when it arrives. That's what we're actually going to solve today. Not the textbook version, the real one. The one where you'll understand, by the end, why the device in your pocket, the sun in the sky, and the electron you just imagined shaking in your hand are all doing the exact same physical trick. Before we go further, a quick prediction. When I ask you why a moving charge radiates, what's your gut instinct? Is it because the charge is losing energy? Is it because it's accelerating? Is it because electric and magnetic fields are somehow made of charges? Hold that guess. We're going to test it, and there's a decent chance you're about to be wrong in a very specific, very interesting way. The same way most physics students are wrong the first time they learn this. This channel exists to take mysteries that sound impossible and hand you back a mechanism you can actually verify. Cited, checked, no hand waving, no, it's just quantum, don't ask. So let's start with what we know for certain, because the certainty is where the real strangeness lives. In 1861 and 1862, a Scottish physicist named James Clerk Maxwell did something almost nobody remembers correctly. He didn't discover electricity. He didn't discover magnetism. Both had been known and studied for decades. Coulomb had mapped how charges push and pull on each other. Ampere had mapped how currents create magnetic effects. Faraday had shown that a changing magnetic field could push electrons through a wire. What Maxwell did was notice that these weren't four separate phenomena. They were one phenomenon, viewed from four angles. And when he wrote the equations connecting them properly, something extra fell out of the math that nobody had put there on purpose. The equations predicted a wave, a self-sustaining disturbance where a changing electric field creates a changing magnetic field, which creates a changing electric field, which creates a changing magnetic field, forever, propagating through empty space, needing no wire, no medium, nothing to push against. Maxwell calculated the speed this wave would have to travel, using nothing but two constants measured in unrelated electricity and magnetism experiments: the permittivity and permeability of free space. The number that came out was 299,792,458 meters per second. That number already had a name. It was the speed of light, measured independently by astronomers and physicists for 2 centuries. Maxwell did not set out to explain what light was. He was trying to unify electricity and magnetism. And the universe handed him the identity of light as a side effect, sitting quietly inside equations that had nothing to do with optics. This is one of the most quietly explosive moments in the history of physics, and it barely gets a sentence in most classrooms. So here's your first reality check. The popular version of this story says, Maxwell discovered that light is an electromagnetic wave. That's true, but it undersells what actually happened. Maxwell didn't go looking for light. Light fell out of the math uninvited, and it took the rest of the scientific world 25 years to believe it. That belief needed proof, and the proof needed a person willing to build the strangest laboratory in Europe. Heinrich Hertz was a German physicist who, in 1887, built 2 simple devices out of wire, spark gaps, and induction coils. One was a transmitter, essentially 2 brass rods with a small gap between them, connected to a source that could make sparks jump across that gap. Every time a spark jumped, electrons in the rods violently accelerated back and forth. The other device, several meters away, was a simple loop of wire with its own tiny gap. Hertz had no wireless technology. He had no way of beaming anything on purpose. What he had was Maxwell's prediction sitting on paper and a stubborn need to test it. When he triggered a spark in the transmitter, a spark jumped in the receiver loop across the room. Nothing connected them, no wire, no contact, just empty air between two pieces of metal. That spark, jumping in a receiver with no physical connection to the source, was the first deliberately created and detected radio wave in human history. Hertz had proven Maxwell right. Accelerating charges, the electrons violently jerking back and forth in that spark gap, created a disturbance that detached itself from the wire, crossed open space, and delivered enough energy to a distant piece of metal to make electrons there jump too. Here's the detail that gets left out of almost every retelling, and it's the detail that actually answers your question. Hertz didn't just prove that moving charges make waves. His experiment proved something more specific and more useful. A charge sitting still or moving at a constant speed in a straight line does not radiate. Only a charge that is accelerating, speeding up, slowing down, changing direction, throws off a wave that can leave and never come back. Sit with that distinction for a second, because it's the whole answer and almost nobody frames it this cleanly. Go back to your gut instinct guess from a minute ago. If your answer involved the word speed anywhere in it, pause, because you're about to see exactly why that instinct, while completely reasonable, is the single most common wrong turn people take with this topic. A charge has an electric field around it always. That field isn't optional, it's just what having charge means. Wherever the charge is, its field reaches out in every direction, weakening with distance, always pointing toward or away from the charge depending on its sign. If the charge just sits there forever, the field just sits there forever too. Nothing is radiating, nothing is leaving. The field is attached to the charge like a shadow attached to a person standing still. Now move the charge at a constant speed, say in a straight line, forever. This is trickier than it sounds, and your intuition will want to say, surely moving charge makes waves, that's basically what current is. But a charge in uniform motion just drags its field along with it, like a person walking normally drags their shadow along the ground. The field reshapes slightly, it gets compressed in the direction of motion, an effect tied directly to relativity, but it stays bound to the charge. Nothing detaches, nothing escapes to live an independent life traveling through space forever. This is worth pausing on, because it quietly demolishes a very common misconception. Current flowing steadily through a wire does not, by itself, radiate significant energy away as light. If it did, every wire carrying steady current in your walls would be glowing and broadcasting radio waves non-stop, and your circuit breaker would be doing a very different job than tripping for overload. So what's different about acceleration? Here's the mechanism, and I want you to actually picture this, because once you see it, you won't unsee it. Information about where a charge is cannot travel faster than light. That's not a rule someone invented for convenience, it's baked into the structure of the universe. So the electric field you feel from a charge right now isn't telling you where that charge is right now. It's telling you where that charge was a moment ago, delayed by exactly the time it takes light to cross the distance between you and it. If a charge sits still, where it was and where it is are the same place forever. So this delay doesn't matter, the field just looks static. If a charge accelerates, changes speed or direction, then the field lines connecting to it have to change to reflect the new position. But the faraway parts of the field haven't gotten the memo yet, because that update can only travel outward at the speed of light. So for a brief moment you get a kink. A sudden bend in the field lines, a transition zone between the old field configuration, still traveling outward at light speed because it hasn't caught up with the update, and the new field configuration, close to the charge, reflecting where the charge actually is now. That kink is not attached to the charge anymore. It can't be, the charge has already moved on, and the kink is racing away at light speed, permanently disconnected from its source. That traveling kink, propagating outward carrying energy, oscillating as electric and magnetic components regenerate each other, exactly the way Maxwell's equations demanded, that kink is light. This is the actual mechanism. Not charges make light because they're charged. Not moving charges vibrate the ether, which isn't even a real thing. A charge radiates specifically and only when it accelerates, because acceleration is the only kind of motion that forces the field to develop a kink that the charge itself can't keep up with and reel back in. Shake the electron and you force acceleration twice per cycle, speeding up, stopping, reversing, speeding up the other way. Each reversal throws off another kink. String enough kinks together, oscillating at a steady frequency, and you get a continuous wave, a beam of light, or a radio broadcast, or whatever frequency your shaking corresponds to. There's a second layer to this that most explanations skip entirely, and it changes how you should picture what's happening close to the electron versus far away from it. Right next to an accelerating charge, the field is a tangled mess. Part of it is the ordinary field that just wobbles back and forth with the charge and never really leaves, and part of it is the traveling kink starting to peel away. Physicists call the first part the near field, and it fades away extremely fast with distance, drop off a cliff fast. The second part, the traveling kink, fades away far more slowly, which is exactly why it can cross a room, cross a planet, or cross a galaxy and still carry a detectable amount of energy when it finally arrives. Stand close to a radio antenna and you're bathed in a swirl of near-field effects that don't really go anywhere. Stand far enough away and all you're left with is the clean, traveling far-field wave, the actual radiation, stripped of everything that stays behind. This is why antenna designers obsess over shape and length. An antenna isn't just a piece of metal that has current in it. It's a structure engineered so that electrons accelerating inside it throw off kinks that reinforce each other constructively in the directions you want and cancel out in the directions you don't. A half-wave dipole antenna, the classic two-rod design going back to Hertz himself, is built to a very specific length so that the timing of the electron's back and forth motion lines up perfectly with the time it takes the field to update across the antenna's length. Get that length wrong and you're not broadcasting a clean wave anymore, you're broadcasting a weak, inefficient mess, most of the energy trapped in the near field instead of escaping as usable radiation. Now, quick gut check. Does this match the guess you made earlier? If you guessed acceleration, congratulations, you were ahead of most first-year physics students. If you guessed something about losing energy or the field just naturally leaking out, you were close, but you had the causality backwards. The energy loss isn't the cause of the radiation, it's a consequence of it. The electron loses energy because it's doing work to create that traveling field kink, the same way you get tired pushing a swing, not the other way around. This is where the math gets a name, and I promise this is the last formula-adjacent moment in this whole video. In 1897, a physicist named Joseph Larmor worked out exactly how much power an accelerating charge radiates, and it depends on one thing above all else, the square of the acceleration. Not the speed, the acceleration. A charge can be moving at nearly the speed of light in a straight line and radiate almost nothing. A charge barely twitching back and forth, but doing so violently, changing direction fast, can radiate significant power. Speed doesn't create light, change creates light. This single fact, buried in an equation from 1897, quietly explains a staggering range of things you've taken for granted your whole life. And this is where the story stops being abstract. Before we get to the examples, try predicting just one of them yourself. Think about a satellite in orbit, moving at roughly 17,000 miles an hour in a smooth, steady circle. Is it radiating meaningful amounts of light just from that orbital motion? Given everything you now know about acceleration versus speed, you already have enough information to answer that correctly. Hold on to your answer, because it comes up again in a moment. Every radio and television transmitter on Earth works by forcing electrons to accelerate back and forth in an antenna at a controlled frequency, thousands to billions of times per second, generating the exact traveling field kinks Hertz first detected in 1887. Every Wi-Fi router in every home is a tiny, deliberately engineered Hertz experiment, running continuously, invisible, filling your house with electromagnetic ripples, carrying video calls and cat memes at the speed of light. Every incandescent light bulb makes light because heat violently jostles electrons inside the hot filament in essentially random directions. Chaotic, uncoordinated acceleration, millions of tiny kinks thrown off in every direction and every frequency. Which is why incandescent light is a broad, warm mess of colors rather than one clean tone. Every LED does something more disciplined. Electrons drop between specific, well-defined energy levels inside a semiconductor, and that drop is itself a form of acceleration on a quantum scale, producing light at a specific, controllable frequency rather than a chaotic spread, which is precisely why LED light can be tuned to a specific color while incandescent light can't. And the sun, every photon leaving the sun that eventually warms your skin began the same way. Charged particles inside that boiling plasma, colliding, deflecting, accelerating violently in every collision, throwing off electromagnetic kinks by the uncountable trillion, every second, for 4.5 billion years running. Your microwave oven is doing something more targeted. A device called a magnetron forces electrons to spiral rapidly inside a magnetic field, accelerating them in tight circles at a specific frequency, about 2.45 billion cycles per second, tuned specifically because that frequency happens to make water molecules in your food rock back and forth violently, generating heat through friction. It isn't cooking your food with microwave energy in some vague sense. It's cooking your food with the exact same kinked traveling field you learned about a minute ago, just aimed at your leftovers instead of a receiver across the room. Hospitals lean on this same principle in reverse in a sense. An MRI machine doesn't shake electrons to create radio waves. It uses a burst of radio waves, generated by accelerating charges in a coil, to briefly knock the hydrogen atoms in your body out of alignment with a powerful magnetic field. As those atoms snap back into alignment, their own charged particles accelerate just slightly, throwing off a faint signal. A very literal, very small version of the exact mechanism you now understand. And it's that faint returning signal that gets turned into the image on the radiologist's screen. You cannot see inside a living human brain without accelerating charges radiating light. That sentence would have sounded like science fiction to Hertz. It's Tuesday afternoon hospital routine now. Even particle accelerators run into this mechanism, though for them it's usually an unwelcome cost rather than a useful output. When engineers force electrons to travel in a circle inside a synchrotron, curving the path counts as acceleration too. A change in direction, not just speed. So the electrons radiate constantly just from being bent around the ring. This is called synchrotron radiation, and at high enough energies it becomes so intense that it limits how powerful circular electron accelerators can practically be built, because the machine is fighting a losing battle against electrons bleeding energy away as light with every single loop. What engineers spend billions of dollars trying to minimize in an accelerator is the exact same physics your imagined shaking electron demonstrated for free. And that brings us back to the satellite you predicted on a moment ago. Circular motion is acceleration. Direction is constantly changing, even if speed isn't. So technically, yes, a satellite curving around the Earth is accelerating. And technically, yes, its charged particles are radiating an almost immeasurably tiny amount of electromagnetic energy just from that curve. But the curve of a satellite's orbit is enormous, gentle and gradual compared to the violent tight curve electrons take inside a synchrotron ring, and radiated power depends on acceleration, not just the presence of some acceleration. Gentle curves radiate almost nothing, violent curves radiate enormously. If you predicted basically nothing but technically not zero, you were exactly right, and you now understand this topic better than most people who've taken a full semester of electromagnetism and never had it explained this way. Here's the part of the story that almost never gets told, and it's where the human cost actually enters, because Hertz himself did not live to see what his spark gap experiment would become. Heinrich Hertz died in 1894 at 36 years old from a chronic inflammatory illness. He never saw radio used for anything practical. He reportedly considered his discovery scientifically interesting, but doubted it would ever have any real-world application. A quote that historians still argue over the precise wording of, but the sentiment is well documented. 12 years after his death, in 1906, a Canadian-American engineer named Reginald Fessenden used the same principle, accelerating electrons in an antenna, to broadcast the first audio radio transmission ever received, a program that included a violin solo and a Bible reading, picked up by ships at sea that had only ever expected to hear Morse code clicks. Within 4 decades of Hertz's death, that same acceleration of electrons in a wire was guiding aircraft, coordinating naval fleets, and during the Second World War, powering radar systems that gave Britain's air defense a critical early warning edge during the Battle of Britain in 1940. Chainhome, the network of radar stations built along Britain's coast starting in the late 1930s, worked by blasting out pulses of radio energy from accelerating electrons in transmitter towers, then listening for the faint echo bounced back from incoming aircraft. The same traveling field kink, sent out deliberately, timed on its return trip, turned into an early warning system that gave fighter squadrons crucial minutes to scramble before bombers ever crossed the coastline. Historians who study the air campaign generally agree that radar was one of the decisive technological factors in that defense holding. The physicist who doubted his own discovery had any use had, without knowing it, handed the 20th century one of its most consequential technologies, one that, within a single human lifetime of his death, was directly involved in the outcome of a war. It's worth being precise here, because sensational claims about this era get exaggerated easily, and this channel doesn't deal in exaggeration. Radar did not single-handedly win the Battle of Britain. Pilot skill, aircraft design, and command coordination all mattered enormously. What radar did was remove the element of surprise, and removing surprise is, in itself, extraordinarily valuable in a defensive air war. That's the accurate, verifiable version of the story, and it's still remarkable enough without inflating it. That's the trajectory worth sitting with. A man shaking electrons in a lab for the sake of pure curiosity, dying convinced it was probably a dead end, and half a century later, that exact mechanism was saving lives, connecting continents, and eventually putting a phone in your pocket that talks to satellites 200 miles overhead, using nothing but the same accelerating electrons Hertz first coaxed into radiating in 1887. So the next time your Wi-Fi drops, or your phone loses signal for a second, that's not some abstract inconvenience. That's a very literal failure of electrons somewhere to accelerate cleanly enough, or a very literal failure of the traveling field kink to reach your device intact. You are, every single day, standing in the middle of a permanent, invisible storm of deliberately engineered electromagnetic kinks, all originating from the same 19th century discovery that one very sick, very humble physicist wasn't sure mattered at all. Let's bring this back to the electron you imagined shaking at the start. You now know, with actual mechanism behind it, and not just a definition, exactly what happened. Moving it didn't unlock some hidden light stored inside. Moving it forced its electric field to try to keep up with a position that kept changing, and because that update can only propagate at the speed of light, a kink formed, a self-sustaining, self-regenerating loop of electric field creating magnetic field creating electric field, permanently detached from the electron, permanently traveling outward, carrying real energy that came directly from the work you did shaking it. That's why shaking a charge creates light, not because charge secretly contains light, because acceleration forces a mismatch between where the field says the charge is and where the charge actually is, and that mismatch has to go somewhere, at exactly the speed limit of the universe, forever. But there's a problem in this story we have not solved yet, and it's a problem that stumped physicists for over a century, including Hendrik Lorentz and Max Abraham at the turn of the 20th century. And it is, honestly, still not considered fully resolved today by every physicist working on classical electrodynamics. If an accelerating electron radiates energy, it must be losing that energy from somewhere, and Newton's laws say every force needs an equal and opposite reaction. So the traveling field kink the electron creates should push back on the electron itself, slowing its acceleration, exactly the way recoil pushes back on you when you throw something heavy. This is called the radiation reaction force, and when physicists tried to write down the equation for it properly, they got answers that, taken at face value, allow an electron to accelerate before any force is even applied to it, as if the electron can feel the future push coming and flinch early. Other versions of the equation predict an electron just sitting in empty space, with no force acting on it at all, spontaneously accelerating itself to infinite speed for no reason. Physicists still don't have full agreement on which version of the math correctly describes what a real, physical, non-idealized electron actually does to itself when it radiates. It's one of the strangest unresolved seams in classical physics, and it's not some obscure academic footnote, because if the person you send video calls to on Wi-Fi is receiving those detached field kinks, then somewhere in that transmitting antenna, real electrons are physically pushing back against themselves in a way we still can't perfectly describe. Here's a common misconception worth correcting before we close, because it trips up almost everyone the first time they hear this story. People often assume that once quantum mechanics arrived in the 20th century, this whole classical picture of kinks in a field got thrown out and replaced with photons as tiny light bullets. Full stop, end of story. That's not quite right. The quantum picture doesn't erase the field kink picture. It sits on top of it. Quantum electrodynamics, developed in the late 1940s by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, still requires accelerating charges to be the source of radiated photons. The acceleration requirement doesn't go away when you go quantum. What changes is that the traveling field kink gets treated as quantized, arriving in discrete packets of energy rather than a smooth, continuous wave. But the underlying trigger is identical. No acceleration, no photon. That's true whether you're doing 1897 Larmor-style classical electrodynamics or 1948 Feynman diagram quantum electrodynamics. The mechanism you learned today survived the biggest revolution in 20th century physics almost completely intact. That's where we're going next. Not why moving charges create light. That mystery is closed, cited, and settled. The next file is about what happens to the charge itself the instant it creates that light. The self-inflicted recoil that a wiggling electron gives itself. A problem so strange it made some of the best physicists of the 20th century consider throwing out classical physics near a point charge entirely. If this kind of mechanism-first explanation is what you come here for, the research for these takes real time, chasing down the original 1887 Hertz papers, cross-checking Larmor's original 1897 derivation, making sure every claim traces back to something verifiable rather than something that just sounds right. If you want to support that directly, a super thanks goes a long way, and I genuinely read every one. Drop your guess below before the next file goes up. What do you think happens to an electron the instant it starts radiating its own light? Does it slow down? Speed up? Something stranger? Tell me your prediction and we'll find out together exactly how right or how wrong you were. One more thing worth sitting with before you go. Every disagreement you've ever had online, every video call, every GPS signal that told you which street to turn down, all of it rode across empty space on kinks in an electric field thrown off by electrons somewhere being forced to accelerate against their will. There is no wireless world, no broadcast world, no satellite world without that one uncomfortable fact Hertz proved in a cluttered German laboratory in 1887. A charge that changes its motion cannot keep its field to itself. Something always has to leave. The case file on why is closed. The case file on what it costs the electron to let it go is still open, and that's the one we're opening next.